Good day, everyone. My name is Hani Mitri. I work from McGill University in Montreal, Canada. It's my pleasure to be with you today to share with you a presentation on distress blasting. So just give me a minute. I'm going to upload it. So first off, I'd like to thank Professor Abbas Tahiri, who is the chair of the ISRM Commission on deep mining, for inviting me to give this presentation. I would like to first off acknowledge three PhD students, former PhD students in my group, Dr. Bayo Tang, who finished in 2000. After he finished, he went on to industry, spent most of his career in underground mining operations. Dr. Maniram Saharan, who finished in 2004, he went back to India to join the CSIRO, a research center, and more recently he went to consulting in mining. And Isaac Penn, who has been with me for 10 years, did his master's and PhD and postdoc, and he's leaving for industry the end of this month. Thank you guys. Without you, I would not be able to present this work today. And thank you for all your hard work and for your findings that helped us learn much more about distress blasting. I also would like to acknowledge the financial support of the IRSST, NSERC, and more recently MyTax and Valley Canada, who supported the PhD of Isaac Penn. So this is the presentation outline. We're going to start with definitions and geomechanical effects. Then we're going to go into applications. We will discuss a little bit how we can model a distressed material, rock material. Then we're going to present two case studies that we worked on before we conclude. There's also a couple of slides from Maniram Saharan, which he asked me to share with you. So what is distress blasting? So we have two definitions here. The first definition is for preconditioning and is characterized by a light density blasting that is used to create or extend fractures in a working phase. So the key word here is light density blasting and a working phase. Of course, the working phase is perceived to be highly stressed and prone to rock burst. So this type of distressing, we're going to call it preconditioning. And essentially, that's what it is. If you have a working phase that's highly stressed, the function of, or the role of preconditioning is to create those fractures at the face, the immediate face. So this way, the stress at the face A is somewhat reduced from what it is further ahead at B. And by repeating this process of distress holes that are longer than the face advance and loading the toe of the distress holes, the face can advance and the stresses can be continuously reduced at the face. So it's a repetitive process. And what you see here, the distress cycles 2 and 3, and the repeated stress pattern is taking place. One thing about the practice of this type of preconditioning is that the green holes representing the development blast and the blue holes representing the distress blast holes are detonated at the same time for safety purposes. So you continuously fracture the face ahead and you advance at the same time. And there are other applications for preconditioning, for example, in cut and fill mining, overhand cut and fill. You see this is a scenario here where the area in green represents the crown pillar, and the crown pillar is highly stressed with those straight arrows that you see here. So by making drilling a few distress holes, loading them, you fracture the roof, and then the face can advance after the stress is relieved, and so on. Okay, so the effective preconditioning here is characterized and it's been agreed upon that it causes rock fracturing, it causes the fracturing in turn will cause stiffness reduction of the rock, and the high stress concentration is dissipated. Also, the load-bearing capacity of the rock is weakened or reduced, and the rock failure mode changes from sudden, brittle, violent to gradual and ductile. So there's more than one reference that support these statements. Another definition for distress blasting, that instead of preconditioning the work phase, blast outside, elsewhere, to create a stress shadow. So this one is called panel distressing. It's a rock burst control technique in which production type choke blasting is implemented to fracture a large panel in waste rock near a burst-prone pillar. So there are differences between the two. I'll discuss in a minute, but this is the definition of panel distressing. If I take the same example of cut and fill method, an alternative way to carry on with the cut and fill method is to go into the footwall or the hanging wall next to the crown pillar and to find a means to distress a panel so that the high stress concentration in the crown pillar is reduced. So it goes from red to green, and this enables a phase advance or a mining lift. So the stresses are shifted further into the crown pillars, so therefore the distress panel is further extended upward to reduce the stresses in the crown pillar and enable further mining. So that's another application of distress panel. So the implementation of this type of application, panel distressing, you gotta find an axis drift outside the area of interest, i.e. the ore body, and then from that axis drift, drill and load, mostly in a fanning pattern, a couple of rows of distress holes, blast to create a complete fragmented panel of material. So that's in essence the method, and the geomechanical effects are quite different. First of all, it's fragmentation rather than fracturing, and it causes significant stiffness reduction in the panel rock, and as a result, the stress is nearly completely dissipated in the panel. But the goal is to actually create a stress shadow in a nearby pillar of interest. And mostly it is an ore pillar. So a comparison between the two techniques, preconditioning is small scale. It's implemented to create fractures or extend fractures. It's implemented directly in the work phase, and it's treated as tactic, something that you can do every second day. Distress panel, on the other hand, is large scale. It's like a production blast, and the goal is to completely fragment and damage the panel away from a mining phase. However, to reduce the stress in the mining area of interest by creating a stress shadow. And this is something that it would take much more than 2 days to do. It requires careful planning and long time implementation. So we're talking about months. So applications. So early on in our survey, we surveyed a large number of applications. The most common in Canadian mines at the time, at least, it was the mine drifts in tunnels and face bursts to avoid face bursts and face ejections. Also shaft sinking at depth. The corners attract high stresses. This preconditioning could be useful in this applications. Cut and fill mining, we just discussed it. Crown pillar is usually burst prone. And the application of panel distressing. For example, if this is an ore pillar, that is highly stressed and experiencing seismicity. So you'll come in the hanging wall, find axis, form a panel, distress it by production-like blasting, and as a result of this distress blasting, the stresses will wrap around the panel and wrap around the pillar, causing stress reduction in the ore pillar. Okay, another completely different application in coal mining, although it's not the emphasis of this presentation here, is in the prevention of roof bursts, particularly competent roofs. So in long-hole mining, in retreat coal mining, as the face advances and the roof is competent, it holds and it bends and it stores a lot of energy, strain energy. So distressing is applied in the roof by routinely distressing rings of distress holes in the roof to force it to fracture, thereby reducing the energy stored in the roof. The work by Peter Konicek, I took this from his work. He is a specialist in this area. He's done a lot of work in the area. This is not something that I will discuss further in the presentation. It's a completely different application. So early on in the year 2000, we surveyed a lot of mines, Canada, US, South Africa, some in Europe, and we created a database by company, by mine, location, also by application. And it appeared there's a lot of applications, a lot of interest, and a lot of trial and error applications of distress blasting. Some of the examples, Camber-Ridley mining, Canada, cotton film method. What you see here is a distress hole that is 8 meters long. The hole spacing is 1.8 meter. The face advance is 1.5 meters. So the face advance is much smaller than the distress hole. So we hope to create fractures here so that by the time we advance, the new face is fractured. In this particular application, the crown of 1902, as well as the sill of 1802 were being distressed at the same time. You can see here the distress holes running parallel to the vein, inside the vein. Another one from South Africa that we reviewed, and this is for a nearly flat deposit in a gold reef. And these are artificial supports. The face is advancing upward with the green arrow showing the direction of mining. And if you envision here that this is the work face on day one, then the distress holes are drilled for the length of 3 times the face advance. Then the face is advanced with traditional drilling and blasting, leaving the other 2/3 fractured. The next day, another distress hole round is extended for 3 times the face advance, and so on and so forth. Okay. Shaft sinking was implemented. There was a case study in Ontario, 3.7 meter holes, down holes at 45 degrees. Loading, explosive loading was only for half the length of the distress holes, and the explosive location was at the toe. So you can see this is also done to prevent floor burst. So the question is, when is distress blasting required? Do we have to do it arbitrarily, routinely, never, or when? Well, if you're in a brownfield, you have many evidence of the need for distress blasting. Seismic activities is a major indicator. Rock burst damage, spalling, ejection, strain burst activities. All these are evidence that you do need to consider distress blasting or preconditioning. If you are in a brand new project, you need to do some studies to determine if there is going to be a potential for a rock burst or strain burst with the proposed mine plan. But even if you are in a brownfield, you still need a tool to help you understand the current situation and the situation after a proposed distress program. So in all cases, you need to study the strain burst prediction. So you need to adopt one or two criteria by which you can assess the situation before and after distress blasting. So I'm going to give a brief summary of the most popular strain burst criteria, or prediction criteria, I should say. I'm going to start with this method with the strain energy storage coefficient proposed by Kadybisky in 1981. Very popular, a lot of citations, a lot of applications, and it's very simple. What you need to do is determine the uniaxial compressive strength of the rock by testing a few rock samples first, and determine a conservative estimate of what you think is the uniaxial compressive strength. Then do a load-unload test. The load-unload test to a level called sigma A, or sigma A is a percentage of sigma max. Some literature suggests 70 to 80%. The author suggested 80 to 90% of the UCS. And by loading and unloading, you obtain two areas here. Excuse me. You obtain two areas here. The area in red represents the recoverable energy after unloading. And the area in blue represents represents the dissipated energy after unloading. The ratio between the two is called F, and it's a reflection of the rock burst intensity. So if F is very high, greater than 5, meaning that there is very little blue, it means there are very little fracturing happening between 0 and sigma A. Therefore, the sample is considered to be brittle, storing a lot of energy. There's a couple of issues about this method, and they are the following. First, how much is sigma C? So you need to test and test and test to have a confident level of sigma C, because after that, you need to get a portion of it. The second issue, which is a little bit controversial, is the range. How much is sigma A? Is it going to be 70%, 80%, or 90%? We've done all three and we get different results. So there is a need to do a little bit of research. And of course, if you go 80 or 90%, you're likely to fracture the sample because you're relying on an estimate of the uniaxial compressive strength. Nevertheless, the concept of this method is quite good. The second method is primarily for coal. That's the ratio of sigma C over sigma T. And this has been used and applied to coal mining. It has not been demonstrated to be applicable to hard rocks that could exhibit high compressive strength and high tensile strength or low tensile strength. The trend is not very obvious here. We tried to look at it with some rocks that we obtained from bursting mines, and it didn't give us a good indication. However, there is some success with this criteria in coal mining applications. Likewise, for this criteria here, which has also been suggested for coal mining applications, and that's to calculate the time between the peak and post-peak. If it's less than 50 milliseconds, then it's burstable rock. The main issue with this is that it requires displacement control. Displacement control test apparatus, although you might have it, which we do, it might not give you this result because it requires extremely slow displacement control apparatus compared to load control, which is the traditional method of testing rocks. A very popular criterion in hard rock is the brittle shear ratio, or BSR. Essentially, the shear stress, the maximum shear stress, divided by the uniaxial compressive strength. And this has been published and cited numerous times. If this ratio is greater than 0.7, then the rock mass is considered to be burstable, and there is potential for rock mass damage and strain burst. The BPI, or burst potential index, was suggested a long time ago. It's been applied a few times for hard rock applications, and it essentially calculates the area, the triangular area under the uniaxial compressive UCS test, with a simple expression of sigma square over 2E. Now, this is used in conjunction with numerical modeling, where ESR is the elastic energy stored, the strain energy stored in the rock mass, as obtained from numerical modeling. We apply this in 2D applications, which meant that ESR is only one-dimensional. However, this can be expanded to 3D, where the energy stored can be obtained by the integration of the stress vector transpose times the strain. So we have three-dimensional state of stress. And according to this method, if you have a BPR greater than 100%, it suggests strong potential for strain burst. And that's a simple application here of a deep drift. I'm going to present this later on, case study. The BPI is 149%, suggesting the need for distressing around the corners and the corners on the edges of the drift. Okay, so in summary, we have 5 criteria, and essentially 1, 4, and 5 are the most suitable for hard rock. So now we talk about considered modeling. How are we going to model this stress-strain relation of the distressed material? We know that distress blasting creates fractures. These fractures reduce the stiffness, so we need to do something about the stiffness. So the first person who thought of stiffness reduction was Blake in 1972. We did some work in 1989 and 1996 in that era with the rock fragmentation factor, but it wasn't with much success. The reason being that we took into consideration the stiffness reduction, but we did not take into account the fact that when you blast, you dissipate the stress as well. So when Bao Yao Tang did his PhD, we suggested this model to continue to build on Blake's model and introduce another parameter, beta, where beta is a stress dissipation factor. So alpha is a rock fragmentation factor responsible for stiffness reduction, and beta is a stress dissipation factor responsible for stress reduction. Later on in 2004, Saharan argued that the distressed material, although the material was isotropic, becomes anisotropic after distressing because of the preferential crack orientation or fracture orientation being parallel to sigma 1. As a result, you need alpha 1 to alpha 3 and beta 1 to beta 3, different stress reductions and different fragmentation factors. So the interpretation of alpha and beta is very simple. If you are at this point here, where alpha is equal to 1, it means absolutely no stiffness reduction, and beta is 0, absolutely no stress dissipation. So that means no distressing. On the other hand, if you go to that point at the top, it means 100% stress dissipation and complete destruction of the rock. Alpha is equal to 0. In practice, preconditioning would be somewhere in the area of 0.5, 0.6 for alpha and beta. whereas panel distressing, because it's production style blasting, would be in the zone of 5%, 5-10% rock fragmentation factor and 90-95% stress dissipation factor. So Zaharan proposed an isotropic model because he did dynamic modeling of single blast holes under biaxial stress conditions where bi sigma 1 is the major principal stress, and he found that the stress, the induced fractures are parallel to sigma 1. So which means that that the resulting E1 and E2 will not be equal. If you reverse the direction, if you put sigma 1 horizontal, again, you will have the principal fracture orientation parallel to sigma 1. So based on that, he suggested 3 alphas and 3 betas, the anisotropic model. We will come back to this at the end. So moving forward, we will use these 2 models for the case studies. So the first case study I want to present to you is one of a drift development preconditioning. It's based on primarily 3 papers, 2 papers in the PhD of Tang, 1999-2000, and much later on, a paper by my former PhD student, Sainoki et al. So going back to the survey done by Como et al. in our early research in 1997-2000, we identified this case to be the most common in Canadian mines at depth drift preconditioning while development. So we decided to focus on this one as a first case study. So we built a 3D finite element model to model 3-phase advances marked in blue, orange, and green here, as you can see. And these are the geomechanical properties. It's a deep drift at 2 kilometers below surface. The in situ stresses are commensurate with the Canadian shield. These are geomechanical properties. And with this, we did the rock fragmentation factor of 40%, stress dissipation of 60%. So the first thought was to examine different ways of preconditioning the face. The first one, we call it the all perimeter without putting any holes in the middle. The second one is full face as per the Canadian practice. So the second one is full face because the middle ones will be assumed to fracture the full face plus the 4 corners. And the third one is called a sidewall, whereby we have 6 holes, 3 on each sidewall. And with the conservative model that we presented earlier and the 3D modeling, we were able to model the drift development, the advance, and distressing as we go along for the 3 patterns. Before we do any distress modeling, we did an evaluation of the state of stress and energy, and it was clear that the drift condition requires is burst prone and requires distressing. So it's 149%. Then we looked at the post-distressing principal stresses for pattern 1, pattern 2, and pattern 3. And for each pattern, we would take cross sections in the face, and we compare between before and after. So before there were stresses in the order of 220, 240, reduced significantly here, where we take that section. And then we summarize the maximum phase stress at for each case compared to what it was before, and we compare the 3 patterns. So obviously here the perimeter and full face have done the best job compared to the sidewall, and we can conclude that perimeter and full face preconditioning offer equally large stress reductions. So this was like a a simple parametric study just to enable us to compare different preconditioning patterns, whether it's worth it to put holes in the middle or just be happy with holes around the perimeter or just the sides and so on. But the underlying assumption, of course, in all of this is that we assumed homogeneous distressing, alpha and beta. So many years later, we decided to go back to the same case studies, but this time we said we're going to do a granular approach. Okay, it's what we call the 3D static dynamic approach. In other words, we're going to look at the same problem here that we analyzed years ago, and we assumed homogeneous distress material with alpha and beta, and we're going to say, well, let's take a closer look and analyze a single blast hole model, then integrate it into the drift model. And with the single blast hole model, we're going to do it in first static to account for the in situ stresses and the excavation, then dynamic to account for the pressure pulse due to blasting. And based on this analysis, we're going to find the extent of damage, then go back and integrate it in a 3D model, like a fractal 3D model, and compare the phase stresses as a result of the damage we obtain. So what you see here is a detailed of the single blast 3D static dynamic model, whereby the blast hole is 6 meters and we only loaded 0.9 meter of explosives, and this is the blast pressure profile. So we get this type of damage due to the blast hole at different cross sections along the blast hole length in terms of shear failure and tensile failure. We bring it into the model and we run two models. The first model we're going to run with the traditional 3D static, as we did before, with alpha 0.4, beta 0.6. And the new one is with 3D static dynamic to find the equivalent state of stress. And the results is the following. The traditional modeling approach assumes that all of these zones are completely damaged and distressed. Well, the new model, the alternative modeling technique with the static dynamic shows that only localized damage is observed around the drift. And when we compare these two results, we concluded that the traditional modeling approach may give an overly optimistic indication of good distress blasting practice. Okay, so in other words, we wanted to examine the efficiency of preconditioning using a more detailed approach with the 3D static dynamic modeling. And the rock fragmentation and stress distribution factors were adopted to come up with an answer for the traditional model, and we compared it with the detailed static dynamic approach. So it's an important conclusion that the maximum possible damage does not achieve a completely distressed drift phase. And this is why also that a lot of Canadian mines are still practicing trial and error on drift development, because we don't have a fixed assured recipe on preconditioning of a drift phase. The second case study I want to talk to you about today is the large-scale panel distressing, and it's based on 3 papers by Venn during his PhD and postdoc. So the case study is, again, before I start the case study, I will just remind you of the concept panel distressing. So we have an ore pillar that is prone to burst, and there's evidence of strong seismic activities or damage. So we decided to do a panel distress, and this large panel will create a stress shadow and shield the ore pillar, okay, to enable its extraction. So that's the concept. So the case study is one of a a complex scenario of an underground mine whereby the red zones are extracted, the green is mine developments, and the blue is the future stopes to be extracted. Strong seismic activities are observed, occasional rock bursts, and it's 1.5 kilometer deep. So the yellow represents the distress panels that are planned to be implemented in the hanging wall of the ore body. And each one of these would be in the form of a panel of this shape that you see on the left here, with a fanning drill patterns, 2 rows, and completely blasted. And this would be called phase 1, followed by phase 2, phase 3, phase 4, to follow the mine plan. So these are the geomechanical properties of the rock mass. Our linear elastic model, brittle rock mass, in situ stresses to initialize the model. And this is the plan view showing the planned distress panel with respect to the ore pillar in green and the geological structures and the backfill zones. So the initial model, as expected, showed us high stress concentrations around the relaxed zones of previous mining, which is now backfilled. And when we used the BSR ratio, it gave us values greater than 0.7, which could explain why the pillar was perhaps seismically active, because the BSR was high, already above 0.7. So any distress program of that scale needs to be assessed and monitored. And the way this distress blasting program was monitored is through borehole stress cells. So drill a hole in the floor or in the back, secure a stress cells, bond it, glue it, and leave it to measure the stress change. So you cannot measure the stress actually in the current at the time you install it. However, if you do it early enough before distressing and mining, then the stress cell will record any changes happening to the ground. So what you see here is it's a 3D view showing the locations of the stress cells. And some of these stress cells were downhole, others were uphole. And the purpose, as I mentioned, is to measure the stress change. So going now to the numerical model, the 3D, the numerical model can predict the stress state due to a distressing. So the question is, how much is alpha and beta? The X represents the location of the stress cell, and the blue shell represents the computed stress change cell for that particular alpha and beta values. If the X is far from the blue shell, it means poor correlation. If the X is over or inside the boundary of the blue shell, as you can see in the first column here, it means alpha and beta are the calibrated correct values that will render the computer model matching the stress changes by the stress cells. So looking at this picture here of the many trials, you can see that alpha of 5% and beta of 95% gives the best match, suggesting that there is severe fragmentation to the point that the remaining stiffness in the panel is 5%, and there is very large stress dissipation of 95%. A different way of putting this distress blast calibration or modeling calibration is the height of the black bars here, the shortest being the best, because that's the length, the distance between the stress shell and the stress cell itself. So the shortest being the best, which is a 0.05 for alpha and 0.95 for beta. So with this calibrated value, we'll go back to evaluate phase 1 panel distressing, and we'll find that there is huge stress drops around the panel, and there is considerable stress drop in the stopes or in the ore pillar, so indicating a success. Although the stress cells recorded small values of stress changes, in practice, it was high values around the panel and the stope. It's because the stress shells were located far from the distress panel. So the results of this case study is that the best match obtained between the 3D model and in situ stress measurements occur when alpha is 5% and beta is 95%, which means high fragmentation and high stress release. Phase 1 distress panels create a strong stress shadow resulting in a stress drop of up to 10 MPa and successful pillar extraction. Numerical models shows stress and BSR reduction due to phase 1 stress panels. And with that, this is the first case study that we did on phase 1 distressing. So next, I'm going to discuss the effective stress anisotropy and the use of the anisotropic model for distress blasting through the phase 3. So phase 2 was implemented, and phase 3 was implemented in exactly the same way as phase 1, with the concept of panel distressing in this fashion. So what you see here is the picture after the previous stopes have been mined out, and now we're ready to implement phase 3. So like what was done in phases 1 and 2, stress cells were installed, also some uphole and some downholes. So one stress cell was uphole, and stress cells 3 and 4 were downhole. So 1 in the crown and 2 in the sill. So what happened is that when we wanted to interpret the results of these stress holes, the stress increased rather than decreased in stress cell 3 in the crown, in the upper part of the pillar. Whereas in the lower part of the pillar, okay, which is the cell, it went down by 6 MPa as expected. So what you see here is a stress shell, computer stress shell for alpha and beta, the traditional ones that we found before, 5% and 95%. And clearly the one below matches. There's absolutely no problem. But there is a discrepancy with the one at the top. This one is saying the stress has actually increased. And the model is saying if we use alpha and beta of 5 and 95%, it should decrease, but it didn't. At the same time, there was seismic activities triggered by phase 3 blast. It occurred north to the phase 3 blast. And this pattern suggested to us that weaker stress trapping is taking place around the crown relative to the cellar. The cellar got well shielded and the stress dropped, but the crown did not. So we decided to go to the transverse isotropic model suggested by Saharan. So we decided to go sigma 1, sigma 2, sigma 3, creating alpha 1, alpha 2, alpha 3. But we decided to simplify it a little bit. So sigma 1 will create alpha 1. However, in the plane perpendicular to the major principal axis, we can say that E2 and E3 are equal. So alpha 2 and alpha 3 are equal. So it's reduced to finding alpha 2 and alpha 3. So we will use the stress readings above here to figure out alpha 1 and below to figure out alpha 2. So cut a long story short, a lot of parametric studies, a lot of comparison, until we finally found out that alpha 1 can only be 0.5. So that's up from 0.05 to 0.5, 10 times. It was finally determined that the crown panel fragmentation factor in the direction of alpha 1 is as high as alpha 1, 0.5, suggesting room for poor fragmentation. While in the directions of sigma 2 and sigma 3, it is 0.05. So the conclusions of case study 2 that panel distress can be used successfully in seismically active mines as a tool to control rock bursts and enhance mine safety. There is no doubt about it. The use of borehole stresses proves to be an excellent tool. You absolutely need a way to monitor the efficiency of panel distressing, and distress cells proved very useful. The earlier you put them, the better it is. Anisotropic stress response to distressing may occur due to preferential fracturing in the direction of major principal stress, and that's what led us to find alpha 1 different from alpha 2 and alpha 3. Panel distressing requires large-scale choke blasting similar to production blast, and this is very different from preconditioning applications. I would like now to present two slides on behalf of Dr. Maniram Saharan, engineering blasting knowledge and future of distress blasting. So first, only 7 to 14% of the explosive energy is utilized for fracturing and fragmentation in a good blast. Air decking with a stemming plug is an efficient way to enhance the explosive energy utilization. So if you look at on the left here, you see here the coupled charge blasting in blue compared to air deck blasting. The area under the air deck blasting is much larger, which means much better utilization of the energy. So Africa and Europe, you use light charges with air decking and obtain satisfactory distress blasting results. Using the coupled charges in large quantities may result in ground control issues, such as rock mass damage, etc. So the future of successful distressing rests with the use of light charges, air decking, and stemming plug. And I concur with this, particularly for the case of preconditioning, because we want to create fractures, but we don't want to damage the rock mass. The other point raised by Dr. Saharan is about the vibrations. So two blast monitoring, blast vibration monitoring methods, namely scale distance and signature hole, are used to monitor blast vibrations. And unlike production blast, in production blast, you want to reduce vibrations. Distress blasting aims to amplify ground vibrations because you want to create fracturing. So the promising step for a successful distress blast is to adopt the reverse signature hole method and choose a delay which would amplify ground vibrations. So with that, I move to the general conclusion. Distressing is still a bit of an art. Still a bit of an art. There's a lot of science. We've learned a lot of things about the geomechanical effects, consider modeling, implementation, monitoring, examining the efficiency, a lot, but it's still a bit of a trial and error. So the more you know, the better. You need to know about the in-situ stress magnitudes and orientation. And if they change in space, the rotation, due to mining activities, you need to constantly get updated on the new stress magnitude and orientation. We are working on this topic right now with one of my PhD students on the determination of mining-induced stresses and their orientation. Mechanical properties of the rock mass, undoubtedly, we need to know them very well and characterize them, as well as the geological structures and their characteristics. You need good knowledge of seismic activities, seismic source parameters, locations, magnitudes. A good database will help you identify the areas that need distressing. The planned mining sequence is very important. For the life of a mine plan, what is the stope sequence? And a good knowledge of blast design and practice. So with that, I thank you for taking the time to listen to my presentation. If you have any questions, don't hesitate to write to me via email. Also, don't hesitate to visit my website. I have a section on my website on list of publications. Browse and let me know what you need. Also, I have another section on open access or free downloads. You can download a fair amount of material free of charge. Okay, well, thank you very much. All the very best. And before I conclude, this is the list of references that we use for the presentation. And there's also the list of references that came out of this research with my research group over the years. Feel free to reach out if you need any publications or information. All the best.